Plastics are polymers. Polymers are made from monomers, which react in a reaction called polymerization. This can either be done in addition polymerization, where alkenes react together to form a long chain polymer, or they can react in a condensation reaction, and this is where two monomers react together to form a polymer chain and a small molecule, either water or HCl. They are either thermoplastics, which melt when heated, or thermosets, which tend to burn when heated. In polymer cycling, polymers are separated using their sort codes found on their packaging. Here is a list of the sort codes and their uses. These are most commonly used plastics. Of these types, only type 1 and 2, PET and HDPE, are widely recycled. Type 4 is also recycled, but not as much as these two. PVC is starting to be recycled, but there are still some limitations. This sorting can either be done manually on a conveyor belt, where people go picking out the PET and the HDPE and PVC and other plastics, and then all the plastics that can't be recycled are put into the waste. There are two types of recycling plastic. There is mechanical and feedstock. In mechanical, you mix everything together and shred it and put it through this process, which is described in this diagram, and then you get out a resin. However, this resin is not very good, as it can only make timber-like substances, and it's a mixture of all the plastic waste. It's not a pure substance, so it can't be used again effectively. In feedstock recycling, there is many different methods. However, the most common methods tend to be chemical depolymerization and thermal decomposition. Chemical depolymerization involves the breaking down of bonds to form back into the monomers. Therefore, it's only liable to use for condensation polymers that we have, such as PET and polycarbonate polyurethanes. To understand how the chemical depolymerization works, I'll look at PET. For PET, we have to understand how it is made. It's made in either two ways. Here's a reaction scheme for it. It's made by either reacting TPA with ethyl glycerol in a condensation reaction, or reacting DMT with EG, and they both form the monomer bis-hydroxyethyl terephthalate, which is BHET, and this goes on further polymerization to form PET. PET can undergo several different reagents to form the different monomers that you want in chemical depolymerization. So depending on the reagent, we can either get BHET or DMT, or we can even get other products such as polyols, and we can form polyurethanes and other substances such as polyesters. Glycolysis is probably the simplest and oldest method used. In this method, we get BHET formed. This is by reacting PET at around 180 to 240 degrees with ethylene glycol with a zinc and lithium acetyl catalyst, and then this reacts by diffusing into the polymer, and as the polymer swells, this rate of diffusion gets quicker, and then it reacts with the ester bonds in the polymer and breaks it up. Methanolysis can also be used in PET, however this is at a temperature of 180 degrees to 280 degrees, and about 20 atmospheres to 40 atmospheres. This leads to the formation of DMT and ethylene glycerol, and again it's in the presence of a catalyst, a zinc acetal. It was first used to increase polyester yield, but now it's used in the recycling of PET, and the DMT that's formed is normally put back into production. It normally tends to be purer than the glycolysis products. However, glycolysis, you get more than one product, so you can make more than one new substance, new polymer. Methanolysis is more used for large scale industries, whereas glycolysis is used for a small and medium scale production. Methanolysis tends to need up to 100,000 tons per year to make a substantial profit. This is because it's got lots of safety restrictions on it when you're superheating the methanol to react with the polymer. Whereas glycolysis is more versatile, you can get more out of it. Both of these processes use roughly the same energy, between 40 and 60 megajoules per kilogram. Thermal decomposition is used to break down addition polymers, but it can also be used on condensation polymers as well, but it's not as effective. Thermal decomposition normally produces 4 products: gases, oils, solid waxes and solid resins. These can be further treated to create more efficient products such as fuel gases, reaction gases, naphtha and oil, and these tend to be used just in the fuel industry. This process is sort of the opposite to addition reactions. It's sort of the same radical process, but it's sort of in reverse, and you don't always get the same monomers that you want. There are 3 possible outcomes of thermal decomposition. There's got random scission, which just cuts the polymer anywhere and you get random small molecules or small polymers. There's got end-chain scission, which cuts off an end group of the polymer, and sometimes you do get the monomer, but it's not very often. The third option, where you take off a small molecule from the actual polymer, so you take off some of the side groups like the hydrogens or the chlorines or whatever is on. But this is also quite rare. It's only more used in PVC, whereas HDPE and LDPE will tend to be the first 2. Dybala and his fellows came up with a mechanism to describe what is happening here. Again, there's got an initiation process. This starts the reaction. It's the first cut. And then there's got depropagation, which sort of breaks up the polymer chain, whereas propagation was you're trying to make it up, whereas this one's actually breaking it down. Then there's got hydrogen chain transfer, so the hydrogens can change the position and to form either secondary radicals or some alkenes. And then these secondary radicals can undergo beta cleavage to form alkenes and primary radicals. You can also form branches between the secondary radicals and primary radicals and secondary radicals. And then there's got termination, which ends the reaction. For recycling HDPE and LDPE, we need to use temperatures of above 600 degrees. These tend to bring out the most outcome, the most products. It tends to be a random chain scission that we get, and the products normally formed are heavy waxes and heavy tars, and these tend to be intermediates, and then they're formed into the gases, aromatics, long chain alkenes and alkanes. However, there has got a risk of contamination here. If you have PVC in the waste material, the HCl that it gives off when it thermally decomposes can react with your products and give them a little different structure to what you was expecting. HDPE is recycled into plastic lumber, tables, benches, but it doesn't actually go back to its original product. You can't get more HDPE out of recycled HDPE. You can only get a different structure. However, plastic recycling is not that worthwhile, as chemical depolymerization only recycles 15% of the plastic waste, and thermal composition creates a different product to the starting materials. Also, councils themselves do not have all of the facilities required to recycle every type of plastic. Therefore, plastics have to be moved elsewhere before they can be recycled. Also, however, recycling of plastics is needed, as our consumption of plastics is rapidly increasing. In 2006 we used 100 million tonnes of plastic, compared to 1950 when we only used 5 million. Therefore, while some other forms of recycling, such as paper and glass, are more effective, plastic recycling is still needed if we are to meet the demands of the future.